I'm Abhisek Panda. I'm a PhD student in the Department of Computer Science and Engineering at IIT Delhi. Today I'll be presenting my work titled FaaSImage and Efficient Image Manager for FaaS, Function as a Service. This work was done under the supervision of Professor Smruti R Sarangi. This is the outline for our presentation. Let us start by discussing what is the problem statement that we are trying to address in this paper. Let me first explain how a typical serverless platform operates. When a user submits requests for three functions F1, F2 and F3, the platform retrieves the sandbox image for each function from a remote registry. It then launches a sandbox inside which the function is executed and the response is returned to the user. The same process is repeated independently for F2 and F3. Compared to conventional cloud platforms, the sandbox creation lies on the critical path of request execution in serverless systems. This process involves two main steps: fetching the function image from a remote registry and creating the sandbox. To reduce sandbox initialization latency, prior work has explored techniques such as sandbox reuse, sandbox sharing, lightweight isolation mechanisms, and snapshot and restore approaches. In this paper, however, we focus specifically on the image fetch operation. Let us now look at some observations reported by commercial cloud providers. A recent study by Microsoft shows that nearly 50% of serverless functions exhibit significant variability in their inter-arrival times. As a result, the likelihood of a function's disk image being available locally is low, since images are quite frequently replaced in the system. Given this is the state of our serverless platform, when we get a request to execute function F4, we first make some space on the disk so that F4 can be stored from a remote storage system. And then we spawn a sandbox inside which the function gets executed. Alibaba Cloud has reported that in the Shanghai region, 86% of the image pull operations take at least 80 seconds. This observation has motivated us to design a image management system that can significantly reduce the image pull latency. Now let us discuss the motivation and drawbacks of prior work. Before discussing the motivation, let us first understand what a function image looks like. In Docker, an image is organized as a stack of layers where each layer contains a portion of the disk image. These layers can be broadly divided into two categories or the two segments, the base segment and the app segment. The base segment includes the files related to the operating system, runtime, and necessary packages. And this segment is shared across function images that use the same runtime environment. In contrast, the app segment stores the file which is very function specific, that contains the libraries, dependencies, and the code. Let us understand how an image pull operation works in Docker. When an image is pulled from a Docker registry, we perform two main operations. That is, the download operation represented as D in this figure and untar operation represented as U in this figure. The download operation fetches compressed layers from the remote registry, while the untar operation decompresses this layer. In Docker, download operation happens or occurs in parallel, but the untar operation happens sequentially. The reason is because if we perform the untar operation parallelly, it might lead to increase in the CPU usage. Our characterization shows that the image pull latency for functions in the function bench ranges from 2 to 43 seconds, which is on the higher end. Since serverless functions typically execute in subsecond timescales, image pull latencies on the order of seconds can significantly degrade the overall performance. While characterizing function images, we focus on three key questions. The first is, what is the relative contribution of the download and untar operations to the overall image pull latency? We observed that for smaller images, the untar operation dominates the pull latency. However, as the image size increases, the download cost becomes the dominant factor. Second, how much an image is actually accessed by a function during execution? Our analysis shows that the functions typically access only about 12.5% to 64.7% of the image during the startup phase. For example, in a face detection workload using OpenCV's hard cascade classifier, when a function executes, it only accesses the files related to the classifier and the image pre-processing, while the remaining OpenCV components or features remains unused. So this observation motivates us to store only the required subset of files initially and fetching the remaining files on demand. Finally, we examine the redundancy across image layers, that is the library layer. We find that approximately 37.3% of the library files are redundant across images, which motivates the use of a shared library layer to reduce redundant data transfer. Now let us discuss the limitations of prior work. The first type of work is layer fusion, where the goal is to maximize the number of shared layers across function images. The drawback of this technique is that in this approach, we are fetching all the files of an image, but we have observed in our previous characterization that a function never utilizes all the files present in the image. Therefore, this leads to wastage of resources during the function image download. The second kind of work is on-demand download, where the idea is to fetch files when they are accessed for the first time. In this scenario, the image pull latency is lower, but when a function attempts to download a larger fraction of the disk image or access a larger fraction of the disk image during the container startup or function initialization stage, this will lead to longer cold start latency. So now we will discuss how FaaSImage is solving the drawbacks of the prior work. Now we'll discuss the design of FaaSImage. In a typical serverless platform, the user submits the function code along with the details of the required runtime environment to the image builder. The image builder constructs the function image with the given information, and we extend this image builder with the profiler that identifies the set of files accessed by the function during the startup phase. Let us represent or refer this profile information as the trace file. The container, the image and the trace file is then forwarded to the refactor engine. The refactor engine separates the library files and stores them in a shared library partition, while the remaining files are packaged into a refactored image that complies with the OCI standards. The serverless platform then pulls the refactored image and the needed library files from the remote registry in parallel. Now let us discuss how exactly the refactor engine works. In this slide, we illustrate the refactoring of two function images, func1 and func2. The refactor engine first extracts the library files and stores them in a common library partition. Next, we apply a FAC module that determines the file placement. Files that are accessed during the function startup are retained within the image, while files that are not required at startup are replaced with remote references that allow them to be fetched from a remote server on demand. Using this process, we then generate the refactored image for func1 and func2. The refactored image and the shared library partition are stored in the registry. When a node needs to pull a function image such as func1, it first sends a request to the registry. In response, the registry returns two components, a trace file which lists the file required during function startup and image metadata which contains the layer IDs of the image along with the libraries needed by the function. The node then determines which layers and library files are missing locally and sends this information back to the registry. The registry responds by transferring only the required components. During this process, two parallel threads are used, one responsible for downloading image layers and the other for downloading library files. Once this download complete, the func1 image is fully available on the node. Now let us see the result of evaluating FaaSImage against the baseline systems that we have discussed in the previous slides. For evaluation, we integrate the aforementioned schemes and our design FaaSImage into OpenFaaS, a state-of-the-art serverless platform. So here we are evaluating these systems using the cold start latency metric, which comprises of three components: the image pull latency, the container initialization latency, and the function execution latency. In this graph, you can see we have this FSI, which represents fast image, and we have GR representing gear, which uses on-demand downloading, and VK, which is representing break, which relies on layer fusion. So when we compare the cold start latency across all the systems, we observe that fast image reduces it by 38.7% on HDDs and 39.8% on SSDs. For the image rotate and the CNN workloads, we observe that fast image downloads up to 32 files during the function execution. So in addition, we also have evaluated the cold start latency of our scheme on three other runtime environments, that is Node.js, Ruby, and PHP, and that is not part of the slides, but yeah, in the paper you can find it out. Now let us conclude our paper. The paper makes the following key observations. The first is a container accesses only a subset of its image during the startup and execution phases. And we observe that there exists a significant redundancy between the library layers of the function images, which have motivated us to have a shared library across the function images. And finally, when integrating FaaSImage with OpenFaaS, we observed that the co-start latency improved by up to 39.8%, and there is up to 45% reduction in the storage space and the download traffic over the state-of-the-art solutions. So thank you everyone for hearing me out, and for if you have any questions or any queries, you can mail it at this email addresses. And also I would like to mention that this paper source code is available online, so for the GitHub link you can find it in the paper. So thanks a lot everyone for your time.